Hello and welcome to the NPTEL online course on microelectronics device circuit. Today we will take up what is known as the MOS parasitics and SPICE model. The name of today's module is MOS parasitics and SPICE module or SPICE model. In our previous discussion into our interaction, we had seen the second order effects which are related to MOS devices, which primarily means that what do you mean by drain induced barrier lowering, punch through. We have also seen the substrate effect or a body bias effect. We have also understood what is the meaning of velocity saturation. Under what limits of operation do we have second order effects coming into picture? What is the reason why these second order effects come into picture? What are short channel effects? How does threshold voltage gets affected by these short channel effects? Why this is important to study? Because when we move ahead in our course, we will see that these influence the output electrical characteristics of the device, and as a result the circuits get influenced by these variations. Now, another important variation of a device or important parameter of the device is its parasitic, which means that those parasitic resistances and capacitances which the device has already inbuilt into it, but they appear to you at certain frequencies of operation, thereby limiting the usage of the MOS devices at those frequencies. So, in order to incorporate all those things and understand the basic concepts of MOS device and therefore give you a basic feel of basic SPICE models which are available to us, let me explain to you therefore the outline of this current talk as far as MOS device is concerned. We will look at the MOS structural capacitance, which means that we will look into the fact that how a MOSFET structure, the very fact that it is structurally designed will give me various capacitance values associated with it. Those things will be clear to you. We will look at MOS therefore overlap capacitances, various overlap capacitances. We will be looking at junction capacitance and channel capacitance, right. This capacitances, which is basically MOS overlap, is primarily because of problems with fabrication and so on and so forth, but channel capacitance and junction capacitances will always arise even with one of the best fabrication facilities. The meaning of source drain resistance should be clear to you as a designer, and then we will be entering into what is known as a SPICE model for MOS devices, right. SPICE is basically a circuit simulator which is being used quite often by large number of people across the world. Most of the versions of SPICE are open source and can be downloaded from the net and can be used by you, and therefore understanding that within the SPICE how does the MOS work, or what is the equivalent circuit model for a MOS device within the SPICE should be understood, and that is what we will be taking up at these MOS devices, equivalent circuit models, and then we will look at level 1, 2 and 3 of model equations of MOS device, right, and see how. So, each level will actually refine the drain current characteristics. So, you should be able to understand the various level and how it works in terms of its working principles. Let me now come to MOS structure and its capacitance. Now please understand, when you are working with a DC bias or when you have applied a fixed value of voltage either to the gate, drain or source terminal, then of course omega is equals to 0, and therefore or the frequency of operation is 0. Xj, if you remember, for a capacitance is 1 upon j omega c, and therefore xj is infinitely large for omega equals to 0. So, for a DC bias, for a DC, I can afford to basically let them behave like a open circuit, right, like an open circuit. So, when you are dealing with DC biases, any capacitances within any of the networks, right, any electrical network can be made as open circuit, because the concerned impedances are infinitely large and therefore you open it, right. When you open it, fine, then you do not have any other place to go, and therefore there will be a current flow, and this current flow will depend upon the network parameters. Whereas when you have a variable in the frequency, which means that you are working in the AC domain and the frequency of the AC signal is varied from some x to y value, it is varied, then this xj, which is the capacitive impedance, right, and assuming it to be infinity when you are applying a DC, does not hold good. So, you will have now a finite, right, xj or a finite impedance, and as a result we have to replace this by sort of a resistive element, which is basically frequency dependent resistive element, and that is the problem area of a MOS structure. So, when a MOS device you are working in a DC domain and try to find out the IV characteristics, well, doesn't matter because you are varying the value of DC, and for all DCs these are open circuitry, and all the discussion which we had for the previous few introductions will hold good. But let us suppose that you are doing an AC analysis or you are doing a transient analysis, right. There are three types of analysis which we generally follow. One is known as a DC analysis, we have got a AC analysis, and we have got a transient analysis, right, transient analysis. DC is when you apply a DC biases. So, which means that it is not a time varying bias, it is a fixed bias, and you give a bias and you try to find out the current at those fixed biases. So, you fix the value of Vg, Vs, Vd, and then try to find out the value of Id, and that is what is known as a DC bias. What is a AC bias or AC analysis? AC analysis means you give an input signal which is not DC, but let us suppose a sine wave, let us suppose A sin omega t, and then for these values of A sin omega t you try to find out the Id value in the output side, right, and you try to find out what the Id value is. That is known as AC analysis. What is a transient analysis? Transient analysis is when you do the analysis for delta t and t tending to 0, which means that for a very short interval of time you try to find out the value of voltage or current, provided the applied biases are varying for a in a very fast sense, and you are able to calculate the variations in the value of drain current for those small values, right. So, for all these for these two we will actually be doing a large amount of capacitive analysis. So, you see here that if you look at the MOS device, right, and if you have these are basically known as this and this are basically CGS, gate to source, and CGD. So, you have a gate terminal here, you have bulk, you have drain, and you have source. So, this is a 4 terminal device. Now, if you go back to your previous discussion from a previous discussion knowledge, you will understand that if you have let me help you out in the sense that, let me say that you have a device, and your device is something like this, that your source is here and drain is here. So, I have a source drain, right, I have a gate here, and then I have a bulk metal gate here, right, and I have a bulk here, and this is gate. So, you see this is high charge, this is also negatively charged capacitance, this is negatively charged. So, which means that between these two I can have a CGS, C gate to source. Similarly, between this two I will have CGD, gate to drain. These are overlap capacitances, right. You also have a capacitance which is, so this is CGS, right, and this is CGD, gate to source and gate to drain. You also have a drain to bulk, which means that let me see, so drain, right, you will have a depletion region here and you will have a depletion region here, right. So, you will always have a drain to bulk capacitance here and source to bulk capacitance here. So, this is CDB and this is CSB or BS, right, whatever you want to say. So, this is CSB and CDB which you see. So, this is overlap capacitances, these are structural capacitances which is available to you. You also have gate to bulk capacitances. What is gate to bulk? Because you will have gate potential here and a bulk potential here. So, the capacitance available at this point is given by CGB. So, effectively there are 5 capacitances which influence the AC or the transient analysis of a MOS device, right, and these 5 capacitances are mentioned in this figure. As I discussed with you earlier, so when you have source and drain and they are overlapping through the gate oxide to this is the metal gate, right, this is the metal gate and this is the gate oxide, this is the channel length, this is the T oxide value. As I discussed with you, ideally the source and drain takes place at the edge of the gate oxide, ideally this should be at this edge, right, but practically there is some diffusion, right. Why? Because see you do this doping here N plus region and N plus region by a diffusion phenomena. So, you have a diffusion phenomena, and diffusion is, if you remember, is by very nature you cannot stop at a particular point, it will have some amount of out diffusivity. So, the diffusion will result in what? The diffusion layer being extended towards each other, right, and as a result you are supposed to stop somewhere here, you ended up somewhere here. fine, and as a result you will have some capacitance which is available at this particular point. So, if there is lateral diffusion and because of this you have an extra xd as the diffusion length, lateral diffusion length, then we define CgSO and CgDO as C oxide into xd into W. I suppose you can understand why, because xd is this, W is basically this dimension W. So, W into xd is the area under the overlap region. This multiplied by area per unit capacitance of C oxide, which is over it, will give you the value of CgSO and CgDO, right. CgSO and CgDO means gate to drain and gate to source voltage, and this is known as gate to bulk overlap, and this is gate to drain overlap, and this is gate to source overlap, right. C oxide is given by epsilon oxide by T oxide, which you see, and therefore this is the gate oxide with lateral diffusion length xd available. So, as you can see, higher the value of lateral diffusion, more will be the value of xd, and as a result your CgSO and CgDO will be also larger in that case, which means that their influence over the transient analysis will also be pretty heavy in nature or pretty large in number. Now, let us come to the channel capacitances. Now, channel capacitance, as I told to you, will have to again two components primarily. We have understood CGS, so it is basically gate to source. So, it is gate to this is CG gate, channel source, you have a gate drain, so gate drain, and this is gate body. So, this is gate to channel, this is gate to channel, and this is also gate to channel for 3 regions of operation, for cutoff, for resistive region, and for saturation region, right. As we discussed, cutoff means when gate voltage is almost 0, gate voltage is always less than threshold voltage. At that point of time you do not have any inversion layer available with you, right, you do not have any inversion layer at this particular point, right, but you might have some charges here, and so this charge and this charge separated by an oxide layer will give you rise to CGC, which is basically your CGC, this one, and then you get CGC because when you go to resistive region and your gate voltage is just greater than VGS, but VDS is less than VGS minus VTH. This is this region of operation, right. So, you will have thin layer available to me, but it is still not inverted in fully inverted. In that case you will have a CGC, and now when you have saturation, when drain to source voltage is so large that it eats away into the channel and therefore your effective channel length reduces, you will have a new value of CGC. Now, what people have done over the years is just for the sake of making it easy to understand, they have divided the CGC into two parts. One is towards the source end, one is towards the bulk drain end, and then they say that if the doping concentrations in the source and the drain is almost the same, I would expect to see that the CGC on the source side and CGC on the drain side to be almost equal to each other. One important point which you should take care of is that when you have inversion, strong inversion, then in saturation region, for example, you have a large number of charge carriers here, right, and they act as a screening charge screening mechanism. So, they tend to screen the charge of the gate from the bulk region, right. So, that is quite interesting, and therefore, you will see that the gate to bulk actually falls down, capacitance falls down at a very high value of VDS, because the inversion layer which is there in the middle between at the silicon dioxide interface, they tend to screen out the gate and the bulk charge, and therefore, you do have a drop in the value of CGS, right. As I discussed with you, therefore, these capacitances are dependent on the region of operation and also on the applied potential terminals, right. So, how much potential you are applying at various points, they are depending on that, and then whether you are operating in the cutoff region, whether you are operating in the resistive region, or whether you are operating in saturation region will also be important, right. Okay. In the cutoff region, as I was discussing, there is no channel charge, right. So, no channel charge, hence the total gate capacitance appears between gate and body. I thought this is perfectly clear and very easy to understand, that when you do not apply any, when you have cutoff, there is no inversion layer, and gate to body and gate to channel are exactly the same, because in the channel in any case you do not have any free charge carriers, right. Now, if you therefore plot VGS versus capacitance here, and we will see how it works out, when your gate voltage is very low or in the cutoff region, you Cox is basically oxide capacitance per unit area multiplied by area gives you the total capacitance. So, the total capacitance is something like this. As you go on increasing the value of gate voltage, since more and more charge carrier starts to form, the screening takes place and the potential and the capacitance starts to fall down. So, you have a reduction in the capacitance at this particular point. In the resistive region an inversion layer is formed, right, hence CGCB or bulk is 0. Therefore, the total gate capacitance is distributed equally between source and drain, right. So, let us suppose you had 10 femtofarad as a total gate to bulk goes to 0 and therefore, this breaks down into 5 femtofarad, one goes to the source side, another goes to the drain side, and that is what is basically found out in this region, that you will have equal distribution between source and drain, right. You have equal distribution between source and drain, and this will result in equal charging on the source and drain side, right, and they will be almost equal to each other. Now, in saturation since the pinch off occurs at the drain end, hence all the capacitance is due to gate and source. I think this is pretty clear, because when you pinch off on the drain side, then there are no charge carriers there, because it is all depleted of free charge carriers. So, again the all it is being shared by the gate and the source. So, it goes, so if you look very carefully, the total charge we will see later on, but if you look very carefully below Vt, the contribution is gate to channel bulk, as I discussed with you, but it falls down, see it falls down and it goes something like this, right, because screening effect is there. Beyond Vt, gate to channel for source and gate to channel for drain, it looks something like this, it becomes larger and larger, right. But as the gate voltage becomes larger and almost fixed for a fixed value of gate voltage, I get that the gate to source voltage and gate to channel for source contribution and drain contribution is equal, and therefore, you see it is given as WL by 2. So, half. So, half is supported by, so you had initially starting with WL oxide, you ended up in saturation region, you ended having the maximum value of each one of them to be WL by 2, since they are in parallel. Therefore, I can safely write down plus WL by 2 as the total capacitance, which comes out to be WL oxide. So, you see which was initially the value which is here. So, which means that when the devices were switched off, the whole capacitance was taken care of by gate to channel. As it switches on and goes to saturation, the same capacitance gets distributed between the source end and the drain end, right. So, that is what we have learned from our discussion so far as these devices concerned. Now, what is the junction capacitance? Now, due to the presence of depletion region at the source and drain end, the junction capacitance comes into picture, which is, this is very straightforward and simple way of looking at it. So you remember there was a depletion region here, this will give rise to junction capacitances. I think that is very fair story which you see, right. So, these are the, so if you look very carefully, this is the source and this is the drain diffusion region, and you have a gate region here, and so you will have a depletion region somewhere here and a depletion region somewhere here. This will give rise to a junction capacitance. Of course, maybe I can show it to you is so it is basically a PN junction which is formed, a PN junction depletion region, right. So, if you remember your basic PN junction theory, we can come to know that the expression for the junction capacitance Cj is given as A times epsilon q by 2 NaNd upon Na plus Nd root over upon 1 upon this value, where A is the area of the cross section between the source and the drain side, NaNd the acceptor and donor ion concentration, and V is the applied voltage which you see, and phi 0 is basically known as the built in voltage, right, and V is the applied bias. So, Cjv is basically A times Cj, this factor is basically my Cj0, which means that under 0 bias the junction capacitance. Why? Because even if you do not apply any bias, right, and you have a differential in doping concentration, there will be always a depletion region formed, right, howsoever big or small, right. That capacitance because of that is basically my Cj0. Now, that gets affected by an external bias when you apply a voltage V. So, you can very well see that when you apply a voltage V, if you go on increasing this V, this quantity becomes larger and larger. So, 1 upon this quantity goes on reducing, right, and as a result this whole quantity becomes larger and larger. So, when you increase the value of voltage, right, and you reverse bias it, the depletion thickness becomes larger and larger, and you end up having a larger capacitance which is there with you in case of a PN junction diode theory as well as for the MOSFET theory, right. Let me come to source and drain resistance, very important part in the parasitic part. So, we learned 4 capacitances with us, actually 5. One is gate to source, gate to drain overlap, one is channel, bulk to source, bulk to drain channel, another is gate to channel, right. But the point is that all of them do not show their effectiveness at each bias, right. As the bias changes, the weight of each of the capacitance goes on changing, right, and therefore it is fair to say that the capacitances are not equal and they do not show their effect equally for all the conditions of operation of the device, right. So, this is what you learned from till now, and this is basic learning from a capacitance point of view, and these are parasitic capacitances, mind you, and therefore they restrict your high frequency operation of MOS device. Now, what happens is that when you have a MOS device and you do have a source and gate region, right, and you have a source and drain region available with you, and this is your source, and let us suppose these are not overlap devices and I have got source and drain. Now, then what happens is that or let me make it something like this, something like this. So, you will have electric field or channel will be very largely found below these 2 points, which means that these 2 points will be still left. So, this is known as source resistance, this is also source resistance, drain resistance RD, and this is RS. This, assuming that you will have a contact here and assuming that you will also have a contact here, there will be some finite resistance here, some finite resistance here. Even though this is N plus and this is N plus, I can safely assume that there will be some finite resistance, howsoever small it is. That plus the series resistance gives you the value of RS, this plus this series resistance on the drain side gives you the value of this thing. And the reason you get RS RD is that prima facie, if you look very carefully, here is the point where you apply gate voltage. So, the electric field is very large in the transverse direction between these 2 points. So, the number of charge carriers are very large here, but the number of charge carriers here and here are very small, because you do not have a transverse direction electric field here, and therefore, the resistance offered by this arm and this arm is relatively very high, right, and that is the reason you will see that you have RS RD, which is the basically given by this thing. So, RS RD is given by LSRD divided by W into R sheet plus RC, where RC is defined as the contact resistances, which is basically the resistances between the contact and the semiconductor, and R sheet is the sheet resistance of the device, that multiplied by LSD by W gives you the total value of RSD. You need not worry from where we are getting this formula or how this formula will be used. At this stage it will be enough for you to understand that there will be some finite resistance between source and drain when the device is working either in saturation or in the nonlinear region of operation. Let me come to the last part of our talk this time, and this is basically the SPICE model for MOS devices, and SPICE is basically a general purpose circuit simulator, right. It is basically a general purpose circuit simulator. It was built way back and it is still being used by many colleges, in many industry also SPICE has been used for the purpose of circuit simulation purposes. So, it is basically a plug and play sort of a schematic entry, which means that you have these devices available with you. You just have to click it and place it on the schematic. Schematic is the place, we will discuss this later on, but schematic is the place where you draw the circuit per se. So, when you drag and draw, you actually are picking up the library of that device, right. So, all the equations related to the device are pulled from the library and placed with the device on the schematic, right, and that is what is an important issue which you should keep in mind. There are 3 models or the 3 levels of models which are available to us, and this is level 1, level 2 and level 3, also referred to as MOS 1, MOS 2 and MOS 3 respectively. The MOS 1 is basically is on the IV characteristics of the MOS device. So, remember that square law term where you had got VGS minus VTH whole square. So, mu n C oxide by 2 into W by L into VGS minus VTH whole square. This is the square law for ID. This is used as first law or MOS 1. A much more detailed analytical model of MOSFET is being used is MOS 2, right, MOS 2 model or level 2 model, right. Another model which has been extracted from experimental data, also referred to as semi empirical model, is used as model 3 or MOS 3. Now, second and third, level 2 and level 3 or level 2 and level 3 takes care of short channel effects. Level 1 is basically a long channel effect, and therefore long channel model, which means you have applied gradual channel approximations and you do not have any short channel effect in level 1, but in level 2 and level 3 you have a large amount of short channel effects here, right. The MOS model when you do write a statement in a SPICE, the MOS model is included by putting a dot model statement in a particular simulation. So, when you put dot model and then NMOS, then you write down its values and so on and so forth, you effectively bringing or the model file associated with the particular MOS device onto the schematic level, right, and that is what we are actually looking into as far as SPICE model for MOS is concerned. Now, if you look at the equivalent circuit of a SPICE model, that's which means that how a SPICE looks at a MOS device, then this is how it looks like a MOS device, right, and it looks something like this, that you will have a drain resistance, remember RD, you also have a source resistance RS. Again you have got four terminals, gate, drain, you have bulk and you have source, right. So, there are 4 terminals, out of which these 2 takes care of RS RD. This ID is nothing but MOSFET behaving like a current source, as current source. Remember, MOSFET is actually a current source, it is basically a voltage controlled current source, and therefore the voltage, where voltage, the gate side voltage is my voltage controlled current source, and this gives you that resistance available here. If you remember CGD, gate to drain overlap, you have gate to bulk overlap and gate to source. So, gate to source, right, gate to bulk, right, this is bulk, and you have got drain to gate to drain. So, gate to drain overlap here, right. If you look back on this side, bulk and the gate side, remember you were saying that, as I was discussing with you, you will always have a junction capacitance between the substrate and the base, and that is what is happening, right. You also have a between source and bulk, this is source and bulk capacitance, source and bulk capacitance, and this is basically your drain and bulk capacitance, right. Remember, please understand that it is basically a PN junction diode. If you remember, it is basically a PN junction diode, and PN junction will have P side towards the bulk side if it is an N channel MOSFET, right, if it is an N channel MOSFET, because the bulk side is basically your P type P substrate, and therefore you will have P side coming to bulk side and you have this towards the N side. So, this model of this and this takes care of the VDB, this takes care of the reversed bias drain to bulk, and this takes care of the reversed biased source to bulk, right, and therefore you see that you do have 2 diodes and you have got 2 capacitances which are variable capacitances in these cases, right, and this is the drain current and the drain voltage which you see in front of you. Of course, if you change the polarity or the type of bias, the polarity of the diodes must also be reversed, right. So, for PMOS, the direction of the current source, polarity of the voltages and the polarity of the diodes must be reversed, right. Let me come to model 1 SPICE model equations. Again it is a linear model, we have already discussed this point. It is 1 plus lambda VDS, where lambda is basically my CLM parameter, and it also depends upon the value of VDS. K prime is basically mu n, K prime in this case is basically mu n C oxide, also referred to as a process transconductance parameter. In saturation we have already discussed is K prime by 2 W by L effective, this much value, where lambda is the this thing. Now, to include the continuity between linear and saturation region, this 1 plus lambda VDS is kept common, right. In the linear region, maybe it will be true that lambda will be approximately equals to 0, and therefore this will not play a role, right, but this will play a role in the saturation region. So, we have got 5 electrical characteristics and this completely characterizes the model. So, if I give you the value of these K prime, Vt, lambda, Vth and phi, you will automatically be able to formulate this level 1 SPICE model in a much better manner, right. Let me come to SPICE level 2 model, where in this case the voltage dependent bulk charge must also be taken into account, right, because please understand the bulk charge varies with the applied voltages, and depending on that people have found out a new equation given by this big equation which is used in SPICE. Do not worry, but more importantly that you can see here is that you have VBS coming into picture, which means that the substrate effect is being taken care of in SPICE level 2 model, right, and you do have gate to source voltage, flat band voltage and so on and so forth. The saturation voltage is given by this formula, and ID equals to ID sat upon 1 minus lambda VDS, 1 minus lambda VDS equals to the saturation current. So, if you see, if lambda equals to 0, then I get ID equals to ID sat, right. If lambda is a high value, relatively high value, this quantity is high, 1 minus that quantity will be low, and therefore ID will be relatively high as compared to ID sat, and that is the reason you will always get a current which is something like this. So, this is ID and this is ID sat. ID will be always larger than ID sat for lambda greater than 0, right, and that is how it behaves like a as a non-ideal current source. Level 3 is basically a empirical model, which means that I extract IV from my data from experimental model, and then I try to fit the linear and non-linear equations with those experimental model. We change it and see which is the line of best fit, and that equations is basically known as the level 3 SPICE model, and it is given by this formula here, ID equals to mu s C oxide W by L. This FB is basically my geometry dependent idea, and that varies with the level which is there. Most of the time we do not use level 3, most of the time for our practical purposes level 1 and level 2 is the most seldom used SPICE model file for our practical applications. We come to the last part of our talk, and let me recapitulate what we have done till now. We have understood that we have 3 types of analysis: DC, AC and transient. When you do DC analysis, capacitance do not play a role because they are open circuited. When they play a role when you have a AC analysis or transient analysis coming into picture. SPICE has been quite useful as a general purpose circuit simulator for a long time, and we should therefore know what MOS model files are used in the SPICE in order to simulate the current versus voltage characteristics. We saw there were 3 basic level files, there are many, but for your understanding at the basics level, you have level 1, level 2 and level 3. Level 3 is much more of an empirical model, based on empirical model. Level 1 is primarily a large your channel length, your gradual channel approximation, which means your lengths are typically large. Level 2 takes care of VSB, which is the source to bulk, and therefore substrate bias mechanism, and therefore short channel effects into consideration. So, level 2 and 3 takes care of short channel effects, level 1 do not take care of it. So, with this we have understood the basic fundamental principles of basic idea of SPICE model files at least, and understood the requirement of capacitances and parasitic capacitances and resistance in this formula. I hope I have made this clear. Thank you very much and for your patient hearing.